In this chapter, I'll cover some of the more advanced rendering capabilities in Hoops Visualize. Some of these have to do with influencing the appearance of objects, so going beyond what was covered in the previous section on materials. And some of these influence how Visualize will draw the scene in terms of the algorithms it might use. So the first thing to cover would be hidden surface removal. There's a variety of different algorithms, the most common of which many people are familiar with, called Z-buffering. That's simply what Visualize will use to figure out how to make sure 3D objects are drawn to the screen with the correct depth, proper Z ordering, as we can see in this medium-sized mechanical CAD assembly, just pretty standard 3D rendering. And another very common type of rendering algorithm is something called hidden line removal. This is a technique to generate pictures with the hidden lines not being drawn, so we can just see visible lines. And Hoops Visualize has quite a bit of control over how to draw hidden line scenes, particularly the algorithm that can be used. There's a couple different types of algorithms. One would be an accurate analytic hidden line removal, which will take a lot more time. It's a little bit more computationally intensive. That's good for going out to 2D or hard copy devices. But when we go out to the screen, Hoops also supports more optimized types of algorithms. And we are able to achieve these with some more advanced 3D shading techniques. So here we're doing a hidden line produced scene to the on-screen display. And as we saw in some of these sample images, some of the advanced capabilities we support is Visualize can also support the lines that were hidden or that would have been hidden had we drawn everything. And we can see here that they can be drawn with a different color or, different visibility. We can influence the dim factor. Then there's also some other controls over how to draw the hidden lines. Another capability that has a little bit more advanced support would be lighting. So the most common lighting algorithms most people are familiar with: flat, Gouraud shading, and Phong lighting. Visualize, however, also supports some additional advanced effects. We have this sort of what we call hemispheric lighting. So that is a type of global illumination. So you can set the ambient light up and light down components. And we also have a capability called eye dome lighting. This is for scenes that have only vertices, so point cloud models. So typically point cloud models would just be drawn as you see below. They're just dots, and all we typically could draw where the dots are just single solid colors. But if those dots also have some normal information, we can simulate and calculate as if this point cloud was a smooth shaded surface and generate the result that we're seeing here. Another capability we have with lighting is the ability to sort of simulate what we call a high dynamic range effect, and we refer to that as bloom. So as we see here, we're kind of blowing out the specular highlighted areas of this model. Okay, and there's some other control over the bloom effect. All right. Another capability would be color interpolation. So this is a capability that allows you to specify colors either by value, by RGB value at vertices, or by color map index value at vertices. And then Visualize will either interpolate across the colors in the color space, so smoothly between one color to another, or across the colors in the color map. And that gives you a wide variety of capabilities. So here's one example of just what we call color interpolation. Here's just color map index or color index interpolation, and here's a hybrid of both. This allows you to map other types of non-graphical scalar data on top of these shells or mesh primitives. And as a result, we can also then draw contour lines in between the hard bands in the color map index, as we can see here. And there's a lot of control over the contour lines, their colors, their weights, their visibility, of course. and I can pull up a sample model. This would be a finite element analysis model, so a highly meshed model here of an engine block. And as you can see, we have a color map, and this might be representing something like stress or pressure or temperature, what have you. And in this case, we're interpolating across both the colors in the color map and smoothly between each color in the color map. So we're doing color index interpolation as well as color interpolation. Visualize also supports some advanced edge attributes. So there's a couple different filters to determine, rather than just draw all edges, we can draw perimeter edges as defined here. You can read about the different classes of edges, or what we call silhouette edges. And a good example of silhouette edges, again, going back to one of our sample models. We can draw silhouette edges in a view-dependent fashion. And two different techniques. One would be an analytic technique where we actually look at each edge and see if it has two attached faces, one of them being visible, one of them not being visible. That would be a silhouette edge. And in this case, we're using something called fast silhouette edges, which uses a shader-based technique and looks at the frame buffer and, the depth buffer. So sort of discontinuities between the z values in the drawn objects and the z value of the background window. So it allows us to very, very quickly calculate on each frame in a linear time the silhouette edges. And it gives a nice effect. This effect can also be called into play if we are in hidden line mode. So we're just drawing regular hidden lines. And if I also turn on the silhouette edge effect, we'll get a little bit more of a thickness. And when I talk about this, we're actually turning off all the edges that meet the filter of silhouette edges right now, and then we turn it back on. You can see those. This can really give a great result, particularly when going to hard copy display, using silhouette edges in combination with hidden line mode to give a much more accurate hidden line display to hard copy or off-screen 2D devices like 2D PDF or PostScript or what have you. And finally, another advanced type of rendering effect I'd like to call out here would be shadows. And there's a couple different classifications of shadows. We'd say simple shadows is referred to as a shadow where we're just having something cast a shadow on the floor, let's say a particular shadow plane, like a ground plane. And shadow maps refers to what I also call inter-object shadows, so objects casting shadows on each other depending on the location of the light or lights in the scene. And finally, we have something called localized shadowing, supported by this technique called ambient occlusion. That's shader-based, and it's sort of in hollows or cavities where objects have curvature in them. We can create this kind of fake localized shadow effect, as if you were like looking in the corner of a room and saw some shadows. So we'll go back to our model here, and I will zoom to fit. And go back to shaded mode. And visual effects, I'll turn on our simple shadow. So we can see here we have a simple shadow on the ground, drop shadow on the ground plane. And then I can go ahead and turn on shadow maps. We have to calculate those. And you can see now that we have localized shadows. Objects are casting shadows on other objects based on the current light direction. These could be dynamically moved over time. For example, if I was, right now the light is in a fixed position as I orbit the camera, but let's say I had the light moving relative to my camera orbit, then these shadows would move. You can also control the quality of these edges of the shadows, and that will have an influence on rendering performance as I interact. And then finally, another type of shadowing, as I mentioned, would be what we call ambient occlusion. So I'll turn off these intra-object shadows, inter-object shadows, shadow maps, and then turn on ambient occlusion. If we look closely, we can see some localized shadowing here going on. Okay, we can look in these in this turbine engine inside the fan blades, and I'll turn it off again, turn it back on. You can see it by the bolts and whatnot, a lot of localized shadowing. So if we turn on a lot of these different effects, the combination of the soft self-shadowing and the inter-object shadowing with bloom and silhouette edges, we can get a very interesting kind of real-time photorealistic type of rendering here. Looks really, really sharp. You can save this out to an image. It could be used for kind of mock-up of a final produced model for higher quality renderings. Okay. And a couple other final things I'd like to cover. This mask transforms rendering effect, it's more of how we handle modeling matrices in cameras. And so when we have local modeling matrices on objects, they can have a rotation, scale, or translate component. So if I'm just doing local edits to an object's modeling matrix by scaling it, rotating it, or moving it around, or of course the camera itself can have rotation component, scale component, or location component would be a pan, so orbit pan or zoom. Transform masking lets you either mask out aspects of the camera or aspects of the local modeling matrices. So a good example would be if we had a kind of a visual item, like let's say a triad that we had at a center point of an object, and I wanted that triad to stay a fixed size, and let's say the triad's drawn with 3D polycylinders. Well, as I zoom in, maybe I don't want that triad to get larger and larger, so I would mask away the scale component of the transform matrices. Or if I had an object that I didn't want to rotate as I orbited the scene or rotated the object, I would mask away the rotation component. So I would encourage you to take a look at some of our sample code that shows some of this. We have a sample called Mask Transforms in the samples directory. And that also will show, I believe, the next and final thing, which I'll refer to here, depth range. And depth range is a setting where you can instruct Visualize to take 3D objects, and you could have them stay localized, 3D hidden surface removed with respect to each other, but sort of push them in front or push other objects to the back of the scene. And a good example of that would just be to look at some of our other objects here. So we have this axis triad here. And as you can see, the axis triad on the bottom left is always drawn in front, even though it's a 3D object. So that's drawn with proper 3D ordering of its objects, but we use some depth range to make sure that that gets drawn in front. Similarly, the nav cube is being drawn that way. And we could also see the legend bar in our FEA color interpolation example is always going to be drawn in front. So that's a nice technique to kind of give ordering to different localized groups of 3D objects, the depth range setting.